So welcome everyone to the day 2 of inaugural tinyML Asia Technical Forum. I'm Sakya Dasgupta, CEO and founder of Edge Cortex, and I'll be chairing today's session. It's a great pleasure to talking to all of you from Tokyo here. So thanks, Pete. I think Pete Warden does not need much of an introduction in the tinyML community, but nevertheless, very excited to have Peter Warden from Google talking to us in this plenary session, and he's going to talk about tinyML in the developing world. Quite an interesting talk, title closer to my heart as well. Pete is the technical lead of the TensorFlow mobile and embedded team at Google, and was previously the CTO of Jetpack before it was acquired by Google in 2014. And he has been quite instrumental in the tinyML community. So without further ado, Peter, over to you.
Thanks so much, Sakya. And yeah, hi everybody, thanks for joining me. And to start off with, I should say that this talk title should probably have a question mark at the end. This is not going to be me laying out how things are already working. This is much more of a chance for me to try and engage, hopefully with people who know a lot more about particular domains than me, and see if we can sort of kickstart something worth doing in the whole intersection of tinyML and developing countries. Like Sakya said, I'm the technical lead of TensorFlow Micro at Google. And if you don't know that, it's an open source machine learning framework that's aimed at trying to fit machine learning models in really tiny devices. The whole sort of tinyML idea of trying to fit in things that might only have 20 kilobytes of memory free, and it's used for embedded devices. Everything from DSPs and microcontrollers to integrated sensors, because this is going to be a sort of an interactive talk, if there are questions that I can't get to or things you want to ask me after this, feel free to drop me an email at petewarden@google.com. I'd be happy to hear from you. So since you're at the tinyML Summit, you probably know that tinyML is the idea that you can actually run machine learning on incredibly sort of cheap, small, low energy usage devices, and that this new capability is really going to open up whole new uses and whole kinds of things, kinds of products, kinds of applications that we could never have built before. But you might not have been thinking about that in the context of the developing world. But as I've been working with this technology, I've come across some intriguing signs that it might actually be a good fit for some of the problems that really are very prominent in the developing world, and also a good fit for the kinds of capabilities and the sort of energy and innovation that's happening in the developing world. So what I'm hoping to do today is really talk about what I've seen that looks promising in terms of how these technologies might be useful and might flourish in the developing world, and then really try and connect and listen to domain experts to better understand how we might actually turn some of these intriguing ideas into real practical applications that do some good. And one of the things that I want to make clear is that I'm, not considering Asia in general part of the developing world. That's not why I want to talk to you about this. In many areas, China and other Asian countries are ahead of Western countries for a lot of the tinyML technologies that are out there. But there's also a very strong connection between a lot of Asian countries and a lot of developing countries in Africa and in Latin America, for example. So I'm hoping that some of those connections may actually prove useful to help us connect people who could benefit from some of these tinyML technologies in developing countries with some of the suppliers that we would need, like the hardware and the software and the research expertise that we would need to actually turn some of these blue sky ideas into real practical applications that do somebody some good. And I think, as Sakya said, I'm hoping to get questions during this talk. So feel free to just jump in with your questions in the QA tool if you're in Zoom, not the chat. And Sakya or Ira or somebody will, sort of jump in at a good point and sort of interrupt me as I'm going through this stuff, so you can actually, get those questions to me, and hopefully we can have a conversation about what's happening here. So to really ground this talk and to make what I'm talking about as concrete as possible, I actually want to show you a couple of practical examples of how machine learning at the edge has already been useful in developing countries in some very new and innovative applications. There are a couple of videos for this. I'll actually get Ira to play this in a few seconds. But to just tell you a little bit about this before we play the video, Plant Village is a collaboration between Penn State and Google, where we actually built an application that developing world farmers, especially in Africa growing cassava, could actually point their phone's camera at a leaf of a cassava plant, and using a machine learning image recognition model, they were actually able to get not only a diagnosis of what disease was likely to be occurring on their plant, they were also able to get advice about how to actually treat that disease. And all of this with no connection needed, because you often didn't have a data connection out there in rural Africa, or even if you did, you couldn't afford it. So this had to be a completely sort of cloudless solution. So with that background, Ira, do you want to jump in and play the video?
Cassava is a really important crop. It provides for over 500 million Africans every day.
When all other crops fail, farmers know that they can rely on their cassava plants to provide them food. There
are several diseases that affect cassava, and these diseases make the roots unedible. It is very crucial to actually control and manage these diseases.
So we're trying to use machine learning to respond to those diseases.
And TensorFlow is the best foundation for our solutions. The app that we've designed can diagnose multiple diseases. It's called Nuru, Swahili for light, the light that farmers can use to see their problems and find solutions. You wave your phone over a specific leaf, look at it, and if it has a symptom, a box will pop up saying you have this problem. When you get a diagnosis, we have an option for you to get advice and learn about the best management practices.
The object detection that we use through TensorFlow relies upon our team annotating images.
We've collected over 5,000 high-quality images of different cassava diseases for this project. We use a single-shot detector model on a mobile net architecture. It's able to make predictions in less than 1 second.
Instead of having to implement thousands of lines of code, TensorFlow provides a library of functions that allow us to build architectures in much less time.
We need something that can be deployed on a phone without any connection. TensorFlow is able to shrink these neural networks to be able to fit on your mobile device.
The human input is absolutely critical. We're really building something that augments your experience and makes you better at your job.
So with AI tools and machine learning, you can improve the yields, you can protect your crops, and you can have a much more reliable source of food.
AI offers the prospect to fundamentally transform the life of hundreds of millions of farmers around the world.
You can see a product that can actually make someone's life better. This is kind of revolutionary.
Probably see that that's a pretty exciting prospect. Like the idea of actually getting some of this AI into the hands of you know, some of the world's poorest you know, developing world farmers, and actually helping them grow food for their families and their communities. I don't know about you, but that's pretty awesome if we could actually translate some of the work that we're doing into something that has that high an impact. And in a similar spirit, there's a nonprofit called Rainforest Connection, who are also using machine learning. But in this case, they're actually trying to detect illegal logging and actually help communities preserve their rainforest resources using these kinds of AI models. And this one's a bit of a longer video, so I'm just going to play the first couple of minutes and then ask Ira to cut it off after that.
We take an old cell phone, we put it up in the trees, and it listens to all the sounds of the forest to pick up the sound of anything that indicates there's some danger.
Já tem caminhão aqui para carregar as madeiras que estão derrubadas, né? E aqui está a nossa floresta sendo desmatada pelo madeireiro. Tá? No ponto de vista de vocês estão achando bom o que está acontecendo na nossa floresta? Não. Por quê?
Porque está acabando as frutas, não tem mais árvores.
E você, Isaac? O que você acha?
Estão cortando madeira. Aí não chove muito aqui.
So again, that's another use case where there's this pressing need out there in the world where having the technology that we've been building, this AI that we're working on, can actually help this very, very physical, real, urgent problem out there in the world that, you know, I'd never thought of it being used for like audio detection of chainsaws and things like that. But once you get this technology into the hands of people who deal with these sort of problems, they think of these really interesting solutions. And there's actually kind of a quiet revolution happening in the, especially around ecology and wildlife. If you go to wildlabs.net, you'll find this whole community of nonprofits and researchers and technologists who join together to try and share their knowledge and build really useful things around helping to monitor wildlife, helping to protect wildlife, helping to protect ecosystems. So like this stuff is starting to happen, but what's interesting is that both of the examples I showed you there are using smartphones. So in the case of the cassava diagnosis, it at least relies on farmers being able to charge their smartphone every day. So you still need some infrastructure and you need some human intervention. You've still got very much a human in the loop in terms of having to, you know, maintain this resource. And with the rainforest connection, they're using smartphones as standalone devices. But one thing you might not have been able to see is that that means that they have to have pretty big solar panels in order to charge up these smartphones. And they have to be in places that can actually get enough, enough sun, enough power. And they're also pretty conspicuous, and they're pretty expensive. Even cheap Android phones, you're talking, at least tens of dollars, maybe $100 per device. So as we know, the world of tinyML is really interesting because it tackles a lot of those constraints. We're trying to ship on devices that might only cost 50 cents and that might be able to run on a coin battery for a year, and that can be small enough that they could just be, concealed very easily, in somewhere like a, rainforest canopy, or they could be placed in fields, amongst crops, fairly easily. And to really sort of try and drive this home, this is, on the left, we have the smartphones that are the existing solutions for a lot of these real-world problems. They require these large, solar panels or very large batteries. They're hard to install. They're expensive. Smartphones are not designed to be in very harsh environments. They're designed to be where people are, and that's the opposite to a lot of the embedded devices that we work with. But the key thing that makes them very attractive is that they are very easy to program, especially compared to embedded devices. Whereas for a lot of these potential applications out there in the world, in terms of ecosystems, agriculture, you have these embedded devices that are really good fits for those environments. They're very hardy, they're very cheap, they're very small, they can run on very small amounts of energy. But the big sticking point is that even for just normal applications, they're very hard to program. And doing machine learning on these devices, which is what the applications that we were just looking at require, adds this whole other level of complexity to what you need to do there. So what sort of things have become possible? I think just going over some of the things that we just looked at, listening out for things like chainsaws or trucks, or other signs of human encroachment on these ecosystems. If you think about what we could do as people, if we can hear those things and we can recognize those things, so they're good candidates for actually building audio models. We can also think about, especially in developing countries, voice interfaces are often very, very important. There's frequently a lot of challenges around using text-based interfaces. The use of voice interfaces on phones is very high in the developing world, especially because there's often a very large variety of languages that people use in their everyday lives. So being able to design devices that can actually recognize voice commands, especially if they're actually able to do that with no data connection, no internet, no radio connection required, That's actually a really important convenience, and really opens up the accessibility for all sorts of devices that people would not be able to normally use if we can add that sort of capability. And then there's all sorts of interesting things around the wildlife applications. There's a fantastic group that puts out, based in the University of Oxford, who put out the Audio Moth board, which is this board that's designed for recognizing things like bat calls and bird calls, and recognizing what sort of species, and I believe sometimes even which individual animals are actually making those noises, and using those to sort of tie back into providing data about what's happening in wildlife reserves. One interesting application I actually ran across recently as well was, I guess, that different mosquito species actually have different frequencies of buzzes. So you could imagine creating a a tiny battery-powered sensor that you could stick up around houses and buildings that would be able to tell you when potentially disease-causing mosquitoes are starting to buzz around. Another really interesting area that seems relevant to the developing world is, again, like voice interfaces, doing things like gesture recognition can be a very natural and a very accessible way of interacting with all sorts of different kinds of technology. We have the magic wand example that you can fire up in your Arduino to sort of, recognize what different gestures people are doing. And there's also a whole bunch of things around transporting and logistics that are especially challenging in the developing world. Things like making sure that vaccines are not damaged as they're being moved around sort of large countries on potentially poor roads, and keeping track of inventory and having smart ways and models able to detect conditions that actually matter. And then sort of less specific to the developing world, but a lot of the image-based applications are about counting things, counting people, cars, coming back to the ecosystem sort of use cases. You can think about having camera traps that actually are able to tell when particularly endangered animals are passing through or passing nearby, and help actually manage and protect all of those wildlife resources that are out there in the world. And another thing that's really important in the developing world is just making sure that we have access to basic running water, electricity, and being able to monitor all of that infrastructure in a way that doesn't require itself a whole bunch of infrastructure to be reliable, to be able to report back. So being able to essentially have peel and stick sensors that you can attach to infrastructure and machinery to keep track of how well things are actually doing.
Just to interrupt you, so we have a question coming in related to retrieving data from these tiny sensors, node devices, especially in the node rainforest. So what do you think would be a most practical way to retrieve such data, radios or otherwise?
That is a fantastic question, because one of the things that we know in sort of the tinyML community is how energy expensive radio communications are. And it's also a big challenge, even using things like cell networks in these places. So that means that you can definitely not have a reliable, continuous connection to over radio in most of these places. What I think the big promise of doing tinyML is that you can afford to do something that's a bit more energy expensive, energy intensive, such as some of the emerging satellite connectivity setups that you have. If you're only doing it when something really important happens. So instead of trying to stream back audio and have a cloud server look for particular bird calls or something like that, you could actually set up a sensor that once a week actually sends back essentially a spreadsheet of these are the different birds I heard based on the calls that I recognized, and these are the sort of the times that I heard them. And if you're able to turn the communication problem from being something that you have to do frequently to something that you can just do sort of, once a week, even if the communication potentially uses a lot of battery, because you're duty cycling it so infrequently, I'm hoping that makes a lot of these things possible. But honestly, that's one of the places where I'm looking for help, and I'm looking for people who know more than me, is I see a lot of promising potential solutions for getting connectivity in places where there's no cell networks, and where people probably won't have set up a LoRaWAN or anything like that. But I have no hands-on experience with them myself. So I guess I'd be very interested to hear about anybody who's got experience with those. So did that answer make sense? Were there any other questions?
Yeah, I mean, excellent. There's a related question to that. So typically, if you're looking at very long distances, you would have to also focus a lot on the lower power usage. The power becomes critical. So kind of related to that, do you have any ideas as to how do you build networks that run extremely power efficiently, allowing long distances for communications or sending the data?
Yeah, so honestly, the only everything I've seen, even like the LoRaWAN type stuff, assumes that there's going to be, everything terrestrial I've seen assumes that there's going to be some kind of network infrastructure that people build. Even if like with LoRaWAN, it's kind of a, something that you can build yourself. You don't have to wait on the cell companies to build it for you. I don't see that scaling well. Like, I don't think that we're going to get to a lot of places in the developing world in the next 5 years. I don't think we're going to have 90% coverage of all the places we want to be in the next 5 years, and maybe not even in the next 10 years, which is where solutions that are kind of seen as very niche and very expensive in the satellite world, I'm very interested by them. You can use Iridium, you can get a really cheap or a comparatively cheap low data rate plan through Iridium. You obviously burn a whole bunch of power sending a signal up into space and back. But I've been seeing a lot of competitors to Iridium starting to emerge that seem like they might offer better connectivity. So that's my big hope, is that we don't have to wait 5 or 10 years for terrestrial network companies to provide connectivity in all of these places, that we can rely on some kind of satellite communications. But maybe I'm just being super optimistic.
It makes absolute sense. Yeah. Thank you.
Were there other questions?
None for now. I think
okay.
We can take as they come in.
Yeah. So another thing that makes it, I think, really interesting to look at these in the context of the developing world is that getting started doesn't require a lot of cash. Like, you can actually buy embedded development kits for as little as $15, which is still not a trivial amount of money, but is within the reach of educational institutes, and compared to sort of trying to buy a GPU or some kind of cloud deep learning setup is definitely a lot cheaper. And there are a whole bunch of educational resources out there that instructors can build on and kind of use to help. Either students can teach themselves, or instructors can use to actually create courses and teach their students. So this is really sort of coming, I'm trying to pull together why I think that tinyML is such an intriguing proposition for developing countries. One of the things that that we've seen, especially around Africa, is, where they didn't have any, landlines, there was this explosion of innovation around things like smartphones, in terms of using them for all sorts of things like sending money over smartphones, which is still something that I can't do here in the US. Trying to set, that's anyway one of my pet peeves after growing up in Europe, is that you could just send money over the cell network from bank account to bank account for free. And in the US, that's not quite so easy. But Africa has really outshone everybody in terms of their innovation for what they've been able to do with smartphones. And I think that there's a real chance for something similar to happen with all of these smart sensors and tinyML and all of these embedded devices, because the alternatives often don't exist that we're using at the moment. These, in the developed world, being able to pick up this new technology and make it fill in those gaps that exist is going to be very attractive. And these devices keep working even if you have no data network, or if you don't have any power grid. So they're very rugged, they're very reliable, and that, again, in countries that are still developing their infrastructure and don't have reliable or cheap data networks or power grids, that's massively important. So I think that is another characteristic that makes them a really good fit. And like I was saying in the previous slide, it's comparatively easy to get started with these devices. You don't need a whole lot of capital and money to start experimenting and start educating yourself and start building these devices and starting to use them for things that are actually going to solve problems in your community if you're living in the developing world. So that, I think, is going to be a very fruitful area where I'm really looking forward to seeing, you know, a lot of innovation happening, not from outsiders coming in and saying, hey, here's what we think you need, but from people in the developing world themselves actually picking up these tools and solving problems for themselves. And there's also this interesting fit between the sorts of things that embedded ML can potentially address and some of the problems that are most acute, you know, across the global south, including things like, you know, clean water and water access, looking for agricultural diseases, agricultural pests, trying to do health diagnoses or health treatment without access to a, you know, a good full medical network. Anything that can actually help on that side is going to be massively important. And also a lot of, you know, the examples we've looked at have been around, you know, ecology and ecosystems and trying to protect wildlife, which, you know, are key issues throughout the developing world. So there's this promising set of, we've got this set of hammers that in the embedded ML side that are very good at solving, these tools are very good at solving a whole bunch of problems that are really present across the developing world.
So Peter, interesting question comes in on that. So, you know, how do people, you know, who want to build applications using tinyML, how should they get started? I think that's a question for many people out there. What would be the best way, you know, programming guides or available hardware platforms? If you could, you know, tell a little bit about that, that would be great.
Yeah, so I'm gonna, you know, push the book that me and my colleague Dan wrote called the tinyMLbook.com. But the nice thing about that book is all of the examples in there are open source, and they include, you can actually just go to the TensorFlow Micro GitHub repo and go into the examples section and find a lot of documentation on them there. And if you have an Arduino, you know, if you're familiar with Arduino, you can actually download the TensorFlow Micro library as an Arduino library in the Arduino IDE. And the examples, like got the magic wand example that I've been working on here, you can just actually choose those from the examples menu and be up and running in just a few minutes if you have an Arduino Nano BLE Sense board. And you don't need to do anything special with ML. You just have to sort of, you know, choose the example and build and upload it. So that's one of the nice things too, is that it's pretty easy to get something basic up and running. And then you can start sort of like peeling the onion and getting deeper into, you know, okay, how do I retrain a model? How do I, you know, gather my own data? How do I take this model and put it into my own application or onto a different board? So hopefully that's useful. I would also, there's some great startups out there like Edge Impulse, who do kind of a lot of this work as kind of a service. You know, they're also a great place to look.
Maybe also a related question that comes in, I think it might be very relevant to ask at this point, is, you know, when we are creating models with traditional machine learning, non-tinyML, data plays a critical role, and typically you have to build your own data sets. In case of tinyML, where should people get these data sets? And if you're collecting your data, how big of a data do you need to get started with tinyML applications?
So what I actually recommend is, if you can, find an existing example that does something similar to what you need. And what we've done for TensorFlow Micro is we've got an example that does a very simple audio model. So it's trying to recognize people saying yes or no. We've got an example that I showed you with the accelerometer. So you're trying to recognize gestures that people are doing on a magic wand. And you're trying to, there's also a person detection model that uses a low power camera and a small image network that fits onto a microcontroller. And those are three of the big domains for running tinyML: audio, accelerometer, and vision. And you can actually, even with a comparatively small amount of data, you can actually look at using transfer learning, as it's known, to take one of those pre-trained models and then just retrain for the data that you've been able to gather for your application, as long as it's kind of fits within one of those sensor areas. So yeah, I wouldn't start off worrying too much about gathering thousands and thousands of data points. I would try, if you can, find an existing example of something that works and then see if you can adapt it through transfer learning to work for your actual application.
Excellent, thank you. I think we also have a couple of.
Oh yeah, jump in.
Do you want to take it now, or we can keep it for
later? No, let's take it now.
Sandeep Kumar asked, how reliable is the model if we are going to quantize the model to 8 bits, INT 8 bits, because we can't build a big network and do a lot of tasks, and there are a lot of constraints on the architecture layer. So essentially, overall, how reliable is the model if we are relying on quantization?
So funnily enough, the quantization, usually, if you do it right, it shouldn't make an appreciable difference to the overall accuracy. What does hurt us is that we often only have very small amounts of storage on these boards. So that means, like for the person detection example, we've only got 250 kilobytes of space for the model. So that means we have to have a version of MobileNet that's a lot smaller than the one that's typically used, which is often, like at least a couple of megabytes in size. So it's not so much the quantization as having to use much smaller models. Now, that isn't as big a deal as you might think in a lot of cases, because you can often also scale down the requirements that you're placing on that model. So for example, for the person detection, the MobileNet model is normally being asked to recognize 1,000 different categories of objects, which is incredibly challenging. What we've been able to do with person detection is say, hey, instead of recognizing, trying to force you to recognize 1,000 different things, can we just have the model tell us whether or not there's a person in the image? And being able to simplify the problem in that sort of way means that we actually get a model that can be up to sort of 90% plus accurate, because we've made the problem so much simpler. So that's really, I guess, is often my answer to the fact that we're working in much tighter constraints, is seeing if we can also simplify the problem so that it doesn't ask as much from the model.
Thank you. In the interest of time, let's move on, and I can
pick
up more questions.
Yeah, definitely. So yeah, coming back to the education side, you know, like some of the things we were just talking about in the answers to the questions, you can actually get started using transfer learning. There's a lot of free Colab notebooks out there that let you train these small models. And the other nice thing is that we're all newbies in this area. You know, none of us have been, you know, embedded ML using deep learning is very, very new. So it's pretty easy to find unsolved problems that are worthwhile working on the research side, and that will be really useful to a lot of other people in the area. So if you're interested in research, it's a great place to be diving into as well. So hopefully I've painted an intriguing picture of the way things might be, but what we have to figure out is whether this is actually going to happen. And you know, one of the things I'm very aware of is that I'm not in a developing country. I don't have much contact with people in the developing world. I don't know what people actually need. So what I really want to do is make sure that the domain experts who are dealing with these problems day in, day out in the developing world have the tools available if they want them to help solve those problems using tinyML if it makes sense. And a lot of that is around trying to provide educational materials and make them accessible so that you know, the people who are facing these problems can actually understand what's happening, you know, what new capabilities are actually out there. And I'm really hoping to hear from those who are working with these problems about what they need so that we can make sure that we're building the right things. So that's, you know, that's my presentation. I'm hoping that I've left you with some, you know, ideas on how we might solve some of these important problems. And I would love to hear from anybody who's diving into this sort of work to, you know, see if there are ways that we can help. So thank you so much for your time, and thank you so much for your questions. I'm looking forward to hearing from a lot of you.
Thanks a lot, Peter, for the excellent talk and also actively taking a number of questions. I think we still have time for perhaps a couple of more questions, or at least one for sure. There's an interesting question from Baku Prithvidar. He says he's working on a medical diagnosis-based problem statement for developing countries, but facing difficulties in gathering data that would be useful for the model in a real environment. He's stuck with animated pictures. So any advice or tips regarding how do you go ahead collecting data for a medical diagnosis type problem?
Yeah, medical issues are especially hard just because of the amount of privacy concerns that there are around these sorts of you know, issues, and also especially for, you know, if it's a Western company that's coming into the developing world, there's a long history of kind of exploitation of you know, people in developing worlds for sort of medical research. So rightly, a lot of you know, people in the developing world are very cautious about, you know, handing over data to you know, these outside companies and organizations. I don't have a great answer for that, I have to say. It's a very challenging, you know, it's a very challenging process, and I feel like with most medical ML innovations, the bulk of the work actually happens in trying to very carefully negotiate and find out ways to get access to the amount of data that you need. So yeah, I guess I feel your pain. I don't have a great answer.
Maybe we have time for just one more question related to the session topic yesterday, which was hardware. So Rafael Shamir asked, any insights on the roadmap for more chip manufacturers? So essentially the role of hardware joining and playing a role in tinyML, especially offering the microarchitectures.
Yeah, and my key ask of hardware manufacturers is that they don't lock down the capabilities of their hardware too soon, because there's still so much innovation happening in terms of the operations and the kinds of things that are showing up in models, that any hardware that was designed 2 years ago is almost certain to, if it doesn't let you reprogram in kind of a generic way, things like activation functions and other stuff, it's very likely that you're not actually going to be able to run models that people care about by the time the hardware comes out. So making sure that the hardware actually has some generic programmability, even if it's comparatively slow, is really, really, my #1 ask.
Excellent. Thanks, Peter, for that wonderful presentation and taking all the questions. I think there are a few more couple of questions, and as you mentioned, they can reach out to you via email. Once again, we would like to thank you, Peter, for taking your time and giving a presentation today.
Awesome. Thanks so much, everybody.
Thank you. I would like to thank our sponsors once again, without whom the tinyML Asia Forum would not be possible and be available for free of charge. Starting with ARM, our premier sponsor, the Software and Hardware Foundation for tinyML. Edge Cortex, their dynamic neural accelerator brings near cloud performance to the edge devices. Finally, sincethe. sincethe builds ultra-low power sensing and inference hardware for embedded mobile and edge devices. Thanks a lot once again to all our sponsors. I would also like to thank our partners, conference partner SHAI, as well as all our media partners. So that brings us to the end of today's session, and I look forward to seeing all of you once again tomorrow for the day 3 of tinyML Asia. Thank you, everyone. Thanks all our speakers and all our sponsors once again. Thank you.